So yesterday we started talking about different properties of functions. The things we talked about were odd and even functions. Today we are just sort of going to keep working on that. Developing and talking about more function properties. Oops. I don't know if this is going to work. Oh boy. That's not what I wanted to do. Okay, properties of functions. That's because I have it on the eraser. All right. So today we're going to talk about the idea of a function either increasing or decreasing. So what does it mean for a function to be either increasing or decreasing? Right? Let's look at the graphs of some functions to sort of illustrate this concept. Right? Now, if we just look at basic linear functions, the idea of increasing, decreasing boils down to, is a function going up from left to right or is it going down from left to right? And that relates to the slope, right? So if I look at just a basic linear function like that one right there, right, I would say this, because this function has a positive slope, this function is increasing, right? On the other hand, a function like this, whoops, so I can't undo it. Let me try that again. So a function like this is decreasing. And I don't have a horizontal line for it. So in general, we're saying that if it's decreasing if the slope, which we often represent with the letter m, is negative, and it's increasing if the slope is positive, right? Now, we haven't really discussed slope a whole lot with functions that aren't linear functions, but we're going to sort of start getting into that. And we also, in addition to having a function be increasing and decreasing, there's a third possibility. A function might be, what do you think?
Just flat.
Yeah, could be constant, right? A constant function would just be, I don't have room for it, so let's put it on the next page here. Just be neither increasing or decreasing. In that case, we'd call it a constant function. So we have a constant function there, not increasing or decreasing. In this case, that's because the slope is 0. So the slope, because we're talking about the slope meaning whether a function is increasing or decreasing, the slope is going to start, instead of just thinking of the slope as sort of a geometric measurement of how steep a line is, we're going to start thinking of the slope as the rate of change of the function, right? A really steep function, right, its y-coordinate, right, let's say a really steep positive function, its y-coordinate is going to be increasing very quickly with respect to the x-coordinate, right? So for a small change in x, you're going to get a really big change in y if it's a really steep function. And so its rate of change is going to be bigger, right? And the same thing is true for a really steep function going down and just steep negative function, right? A function that's shallower, right, or a constant function, in this case right here, which is not increasing that much, does not have big changes in y for the same size change in x, right? And so this whole idea of slope being the rate of change of the function is going to become important, and it's going to tell us whether the function is increasing or decreasing, and how quickly is it increasing, how quickly is it decreasing. So how quickly is the function increasing or decreasing, right? That's what the slope is going to give us a sense of. So with linear functions, it's obvious whether a function is increasing or decreasing. It's just the slope. But they're not linear. consider the following function. So if I have a function that looks like, let's say this one right here. Sort of looks like a sine function, but I'm not going to call it a sine function. It's just going to be some random function. It goes to the origin there. And let's say it passes through the point right here. This point will be 2, 3. And let's see, this is the point down here. Actually, let's get this x-intercept is going to be, let's say, 3, 0. Down here, we'll have this point be 5, negative 2. And the x-intercept over here will be 7, 0. Right? So this function right here, right, is not a linear function. So what that means is, as I follow along the function here, the slope is constantly changing, right? Instead of being just a straight line where the slope is constant the entire time, on a function like this, the slope is not constant. So if a function is nonlinear, it's not a line, right? The slope is not constant, right? It's constantly changing, in fact, like this one right here. And so wherever the function is going up from left to right, we would say it's increasing. And whenever it's going down from left to right, we would say it's increasing. And we want to be able to look at this function right here, which I'll call this function f of x, I guess, and determine where is f of x increasing and where is f of x decreasing. Right, so where is it increasing? And where is it decreasing? Okay. So f of x is increasing on what intervals are we seeing here? And let's assume that because these arrows sort of go down, that it's always going to be going down out to negative infinity in this direction. It's always going to be going up, right? It's always going to be increasing all the way to the right to positive infinity. So can you give me intervals in interval notation for where f is increasing? What do you think, Kevin?
Maybe open negative infinity to close to.
Well, at 2, what's happening? What's the slope at 2?
Oh, okay, yeah, never mind.
Yeah, the slope at 2 is actually 0, right? It's not quite, it's not increasing. That's where it goes from increasing to decreasing, right?
Yeah,
And so if we were to draw like what we're going to later on call a tangent line, right? A line that has the same slope, a straight line that has the same slope of the curve at that point, it would look like that. It'd be a flat line, right?
I was just thinking that people floating the right. That's why I forgot the arrow was going down.
Yep, no, that's okay. And so it's really not increasing or decreasing right at that point, so we're going to use an open interval. And where else is it going to be increasing, Kevin?
At 5.
From 5 to?
Infinity.
Yeah, from 5 to infinity here. And for decreasing, over what interval is it decreasing? Where the slope's negative. It's going down from left to right.
Yeah, so I guess 2 and negative infinity.
2 to negative infinity? Isn't it increasing from left to right over here? It's going up, right? If we follow the function left to right, it's going up, right? Because we always look at it from left to right. So we always move in this direction. So if we're moving in this direction, aren't I going up in y? So it's positive. It's increasing from here to here. It's decreasing from here down to here, right?
Yeah, that's what I said. Okay.
2 to when? To where?
2 to 5.
Yep. So it's decreasing from 2 to 5. And so just by looking at the function, we can identify where it's increasing and where it's decreasing. And so I'm going to give you another function, and I'm going to ask you to tell me where it's increasing and where it's decreasing just by looking at it. So here we have another example of a function that is doing a bunch of different things in different intervals. So let's go ahead and identify over what intervals is this function increasing, and over what intervals is f of x decreasing. Okay. Okay, so looking at this function now, we're trying to identify which intervals that f(x) is increasing and which is decreasing. Someone asked a good question, and let's say that over the interval right here from 2 to 3, we have a horizontal line. Let's say, okay? So f(x) is increasing over which intervals, do we think?
Open, negative infinity, to 2, open, open 3,
Yep.
to open 6, open 8, to open 9, and open 11 to infinity.
Okay, very good. And what about the decreasing side of it, Kevin?
It's closed 4 to 6. Is that 6? Am I reading it wrong?
This
Oh, sorry,
one
sorry.
right, sorry, yeah, this one right here is supposed to be a 6.
Okay, yeah, so it's closed 6.
Yep.
To
Open or closed?
closed.
Is it increasing or decreasing exactly at 6?
No.
That's the
Okay,
question, yeah.
So, yeah, open 6 to.
Here, I
Yeah,
gotta clean that up for a sec. So you said open 6
to open 8,
to open 8.
and then open 9 to open 11.
To 11, yep. And that's it? Yep. And then the interval from 2 to 3 is neither increasing or decreasing, right?
Yeah.
Very good. Okay, next. Local minimums and maximums. So, a local minimum occurs at a point when a function goes from increasing to decreasing, right? So this point right here, let's say this is the point, if this is the next value c, it's the point c, and this is the function f of x, so the y value is going to be f of c. So we would say that the point c, f of c, is a local minimum because f of x goes from decreasing to increasing. Right? And on the other hand, if we have a situation where a function goes from, whoops, let's try that again. On the other hand, if we have a function that goes from increasing to decreasing at a specific point, then we would say that point where it goes from increasing to decreasing, we'll call this point once again c f of c. We would say that that point is a local min or minimum, right? And at that point, f of x goes from increasing to decreasing. Okay, so that's a local minimum and a local maximum. And so a lot of functions have different types of local mins and maxes. And so we want to be able to identify those as well. And so I'll give you a function and just have you go ahead and do that. Say I have the following function. And so this is the function f of x. Let's say this point is 1, 3, and this point is 6, -2, right? We would say that, and there's two ways to ask this question, right? The first question is, where does the local minimum occur, and what is the local minimum or local maximum, right? The actual point is what we call the local minimum or local maximum, right? So the point is the local min or max. The x value is where it occurs. So we think of the x value as sort of the location, and the point itself is the actual max or min. So when you're asked that question, that's how you're going to be trying to answer that. All right, so that means we have a local max at, it's at x equals 1, right? But the actual local max is the 0.13. So that's how we talk about local mins and local maxes. The x value is considered like the location, and the point itself is the actual maximum or minimum. And then local min is at x equals 6, and it is the point 6, -2, where the function goes from decreasing to increasing. Okay. You can also use graphing utilities to locate local maxes and local mins if you don't know exactly where they occur just by looking at the graph of the function. Now, for instance, that happens a lot in the formula for a function. So let's say I have the function 6x cubed minus 12x plus 5, and I ask you to find all local maxes and mins. Right? So this is a cubic function, which you don't actually yet know how to graph. Eventually we'll be able to do that when we talk about polynomial functions in more detail. But right now you don't know how to actually graph that. So you're going to use your graphing calculator to graph it, and then we'll talk about how to use the graphing utility to do that. And essentially we're going to use the function calc fmax and fmin in your calculator. Those functions will allow us to find the local maxes and local mins of a function. So let's go ahead and work on that. So if the first thing you want to do is go into your function and go ahead and graph it, plug it into y equals, and you're going to see that it looks roughly like this, right? And just by looking at the graph of the function on the calculator, you can't really tell where this local max and where this local min occurs. And so to be able to know what the x and y values are of these points, you're going to have to use the fmax, fmin function in your calculator. So the next thing you're going to do is you're going to hit second function, trace, or you're going to hit calc, right? And you're going to scroll down to either minimum or maximum. Sorry, it's actually the name of the functions themselves are not fmin, fmax. Must be confusing now with a different program. There's so many. Instead, it just says maximum or minimum. So if you go to calc, the calc menu, after you've graphed it, and you scroll down to minimum and maximum, those two functions allow you to locate them. So let's first start with the local max right here. So scroll down to maximum and hit enter. And it's going to ask for left bound. So you're going to scroll your cursor anywhere to the left, like maybe in this region right here, anywhere around here, and hit enter as a left bound. And for the right bound, you're going to scroll anywhere to the right, so maybe somewhere in this range right here of that local max right here, and you're going to hit enter. And then for the gas, you can just hit enter one more time, and it will tell you that this local max right here is located at the point -0.816, 11.532. Of course, I'm rounding to 3 decimal places in both cases. Okay, so that's local maximum right there, right? So you can use your calculator's maximum function to locate that, and you can do the same thing with the minimum function here. Once again, hit second calc, but now just hit minimum instead. Left bound, you're gonna want to select any area just to the left of this point. So like any area right here is fine. Just scroll your cursor using the left and right keypads to do that. And then same deal for the right bound. Pick somewhere right over here and select and hit enter again, and then hit enter a third time when it asks for a guess. And it looks like this point is going to be the point 0.816, positive 0.816, and negative 1.532. Right? And this is, of course, a local minimum of the function because it goes from decreasing to increasing. So if we're given the graph of the function, as in previous examples, we can just look at the graph to identify local maxes and mins. But if we aren't, if in this case we're just given the formula, we're going to go ahead and either graph the function. If it's a function, if it's a graph that we know how to graph without using our calculator, we should still do that. But if it's a function like this and we don't, we're going to graph it in our calculator, and we can use the min and max functions in the calc menu to be able to locate these mins and maxes. Okay? All right, so another concept we're going to tackle today in more depth. We talked a little bit about the rate of change of a function. Right? And in a linear function, like this one right here, the slope, right, is constant. So the rate of change of the function is constant, right? The amount that it's going up for the amount that goes out doesn't change as we go along the line in one of these guys right here. And so the rate of change itself is the slope, right? And so let's say I have 2 points in the line, right? Whoops. So I have 2 points in the line. The first point, let's say, is x1, y1. All right, and the other point up here is going to be x2, y2, right? Then my slope, which is my rate of change, is going to be y2 minus y1 over x2 minus x1, right? And that is the rate of change of that function, right? So when we have a constant linear function, we can just take the slope between any 2 points, and that gives us the rate of change. How much is the y-coordinate increasing for a certain increment in the x-coordinate, right? The change in y over the change in x. Now, it becomes more complicated, of course, when we're dealing with functions that aren't linear. So let's say a function like the following. Right? This function is curvy, right? And so its slope is changing as we go along the function. And so we can't just use this slope formula to figure out what is the rate of change at any given point in time. Well, that rate of change is changing. So I have 2 different types of questions I could ask, right? First of all, what is the slope at a specific point, or the rate of change at a specific point in time, right? Exactly at that point in time, and we would call that the slope of the. Later on, we're going to call that the slope of the tangent line. That's a calculus question, really, that we won't really get into this year, but one that's interesting to ask nonetheless. The one that we can't answer right away, though, is let's say that we know that at a certain point the function, this function right here, is at the point, let's say 1, 2, and later on the function is at a point, let's just say that this is 5, 4, right? And so we know where the function is, what points it passes through at 2 different points in time. And let's say we wanted to, instead of trying to figure out the exact rate of change at a specific point in time of this nonlinear function, what if I wanted to just get an approximate rate of change by using these 2 points? And that would be represented by the slope of a, what we're going to start calling a secant line, This is called a secant line. It's a straight line that goes through 2 points on a function, right? And if we take the slope of that secant line, what that's going to do is that's going to give us an approximate or an average rate of change, right, of that function over the interval, right? So the average rate of change of some function f of x on the interval a to b is just going to be equal to the slope, which is going to be f of b minus f of a over b minus a, right? Because these are the y coordinates. This is like y2 minus y1, right? The f of b is the y coordinate at b, and f of a is the y coordinate at a. So y2 minus y1 over x2 minus x1. It's the same formula we used right here, right, for these 2 points. So we're going to use for these 2 points now. I'm just referring to this as, this is x, right, which would be like either b or a, one of those 2 endpoints, and this is f of x. And so how it applies to this function right here, if I wanted to actually get a measurement for this one, the average rate of change of this one right here, I'll put this over in this area. So the average rate of change would be 4 minus 2, y2 minus y1 over x2 minus x1, which would give you 2/4 or 1/2. So the average rate of change of this function right here between these 2 points, between this point and this point, is just the slope of the line that connects those 2 points, right? And that is 1/2. Right? And so we can think of that as the average slope, right? Because it starts at this point and it ends up at this point. The average slope, the average of all, if I took all the slopes, so like at every individual point here, it would be the slope of this line that runs through these 2 points right here. Right? And that would give us the average rate of change of that function f of x. So, what I want you to do in this next one is I'd like you to find the average rate of change of this next function over a couple different intervals. Also, write me the equation of the secant line. So I'd like you to find, for this function right here, this function f of x, if you go ahead and find the average rate of change of that function on the intervals 0 to 2, 2 to 6, and 0 to 6. Go ahead and give that a shot. So if we go ahead here and we identify the average rate of change of the function over these intervals, let's start off with the interval 0 to 2. The rate of change, average rate of change is going to be 2 minus 0 over 2 minus 0, right? So what's the average rate of change here? 1, yeah? So it goes up 1 for every 1 that it goes over. That's how fast the function is increasing. From 2 to 6, the rate of change. Do you think it's going to be bigger or less based on the function? Is it increasing faster? Is it getting steeper or shallower? It's getting steeper, so is it increasing faster or slower? It's increasing faster, right? Because the slope is getting bigger. So if we go ahead and plug that in, we'll get 3 minus 2. Whoops. You know what I did here? I made a mistake. This, based on how the graph looks, it should be 3, 6. Yes, I just inverted my coordinates here. So this should be 3, 6. It's going to make a pretty big difference. So let's change that to 3, 6. Right? So that should actually be 3, 6. Let's go back and fix that. Okay. And so the rate of change is going to be 6 minus 2 over 3 minus 2. So we're expecting that to be a bigger number than 1. It ends up being 4 over 1, which is 4. So that lives up to our expectations. And then lastly, on the interval 0 to 2, sorry, on the interval 0 to 6, the rate of change is going to be 6 minus 0 over 3 minus 0. So that's just going to be, what, 2. Does it make sense to you guys why the average rate of change between 0 and 6 is going to be slightly less than the average rate of change from 2 to 6? Sorry, the average rate of change from 0 to 3, I should say. So, got to change that too, don't I? Confusing everyone here, as well as myself, I guess. Nope. So really, I'm at the interval from 0 to 3 here, not 0 to 6. So 0 to 3. And the average rate of change is 2. And so if we draw a secant line between the two, it's easy to see that this secant line right here is going to be slightly shallower than this secant line that goes through those 2 points. And so the average rate of change, because the slope is bigger for this line, the average rate of change between these 2 points is going to be greater. And it is. It's 4 instead of 2. All right, let's look at another example here. For the following example, instead of finding the average rate of change, I would like you to go ahead and find the equation. Find the equation of the secant line through the 2 points indicated. Okay? So, my hint to you is you're going to want to go ahead and use what form of the equation? The equation of a line. Point slope. Yeah, you're going to want to use point slope to accomplish this. Okay, so if we want to use point slope form to write the equation of this line, we'll go ahead and write it like so. So we know point slope is y minus y1 is equal to m times x minus x1, right? And so let's go ahead and plug that in. So y minus, so first we have to find our slope, sorry. And so our slope is going to end up being negative 1 minus 8 over 6 minus 2. So the slope of our secant line, which I actually drew a dotted line, a poorly drawn dotted line, through those 2 points to show you the slope of the line that we're looking for here, is going to be negative 9 over 4, right? So negative 9/4, that's my slope. And with point slope form, I can choose to put it through either this point or the other point. So either this point or this point I can use. I'm going to use the first one, 2, 8. So it'll be y minus 8 is equal to negative 9/4 times x minus 2. Right? And I just asked for the equation of the line. I didn't specify what form it had to be in. So that is the equation of the line. You can leave it just like that. Okay? So if you're given the graph of the equation of the function that you were talking about, and you want to find the average rate of change between 2 points, or you want to find the equation of the secant line, the previous examples were how you would do that. But sometimes, if you're not actually given the graph of the equation, you're just given the formula for the function. So, for instance, with the following function, if I have g of x is equal to 3x squared minus 2x plus 3. Right, so there's the function. Of course, you can graph it with your calculator, but you're not going to need to use the graph to solve the following problem, which is, first of all, find the average rate of change from x equals negative 2 to x equals 1, right? And then find the equation of the secant line, right, over that same interval, which would be the point, the line containing, oops, that would be the line containing the point -2 and f of -2, or g of -2 in this case, sorry. So g of -2. And also the point 1, g of 1. So we see that these are very these two questions are sort of connected to each other, right? The first one is what's the average rate of change of the function, g of x, from x equals -2 to x equals 1, and then find the equation of the secant line that contains those 2 points. So this is just the secant line over this interval, essentially. So for the first part here, finding the average rate of change from x equals -2 to x equals 1. We know we need more than just the x coordinates to do this, right? We have to have the actual points. So when x equals -2, we have to know what is y equal to for this function. Same thing's true for 1. So we have to figure out what is g of -2 and what is g of 1 to be able to answer that question, right? So g of -2 is going to be 3 times -2 squared minus 2 times -2 plus 3, which will end up being 4 times 3 is 12, plus 4 is 16, plus 3 is 19. And then g of 1 is just going to be 3 minus 2 is 1, plus 3 is 4. So the average rate of change is going to be equal to 19 minus 4 over -2 minus 1. So we'll get 15 over -3, sorry, which is going to be -5, right? So the average rate of change of the function is -5. That's the slope. That's the average slope, right, of the function from -2 to 1, which is the slope of the secant line that connects the points -2, 19, and 1, 4. So find the equation of the secant line containing those 2 points that we just used to find this average rate of change, right? Because these are the 2 points that we found. We found g of -2 and g of 1. So this point and this point are the 2 points that the secant line goes through that has this slope. So we know the slope, right, of the secant line. That's the average rate of change. We have the 2 points it passes through. So we can use the slope and one of the 2 points to write the equation of the line in question. I'm going to use this point right here, so 1, 4. So the equation of the line would be y minus 4 is equal to -5 times x minus 1. Okay, are there any questions about that? So the slope of the secant line is the average rate of change of the function. And it's really easy to find that if you know the 2 points in question. And later on, like I said, we might get to the point of talking about the rate of change at a specific point, not just the average rate of change. But for now, we're just concerned with the average rate of change. Okay, today is families of functions. Sort of summarizing that. And we're just going to sort of play around with them graphically today and talk about their properties. I'm going to refer the people who are watching this online to pages 95 through 97 in your text. This is the library of functions. So these are just your some of your basic, what we call parent functions. Right? Some of your basic parent functions that we're going to be working with from this point forward. And so it gives graphs of all those functions and it talks about their properties. So since we're going to be using a graphing program that's not within this program that I'm able to actually record, I would just recommend for all of you people watching online to go and check out those 3 pages right there, because we're essentially just going to be graphing those and looking at that same thing. Okay? So for tonight is as follows. So the homework for tonight is from the handouts, which I have made PDF versions of and emailed out to everybody. I still do not yet have a copy of the new book, so these are examples from the 5th edition. In any case, this is the problem set for tonight, and we will go over any questions you have tomorrow. And once again, they're from the handout and not from your 6th edition of the book. They're actually from the 5th edition, which you don't have, but I copied those pages that you'll need, and I emailed them out to everyone as a PDF. Have a good day.